All right, so now you know how to find antiderivatives and indefinite integrals. And today we're going to learn how to use these things to evaluate the definite integral. So first of all, recall the fundamental theorem of calculus, right? It says that if you have a function that represents the rate of change of something, so this is the rate, right? This lowercase f is the rate of change of some function, right? Then the integral of that function gives you the total change between a and b. All right, so this is the total change. Total change of capital F of x, right? Between a and b. Between a and b. Okay, that's the fundamental theorem of calculus. But remember that this capital F is the antiderivative, right? If lowercase f is a rate of change of f, then capital F is the antiderivative. And so we're going to use antiderivatives now to evaluate definite integrals. All right, so let's just dive in and take a look at an example here. So we have the integral from 1 to 3 of 2x dx. So the first thing we need to do is find the capital F of x, right? The antiderivative. And the antiderivative is the indefinite integral of 2x dx. All right, and you learned that we can do that. It has to be x squared plus c. All right, so now the integral from 1 to 3 of 2x dx, okay, the definite integral, is just the difference. It's f of 3 minus f of 1. Okay, that's what the fundamental theorem of calculus tells us. So now, because now we know the antiderivative, we can just plug in the numbers. So capital F of 3 is 3 squared plus c. All right, I'm going to put parentheses around it. It's important to put parentheses in a lot of these problems, otherwise you're going to have trouble. So I'm going to put parentheses around the second one as well, and we're going to plug in 1. All right, so we get 1 squared plus c. Okay, now let's just simplify that. So we get 9 plus c, and I'm going to distribute the minus sign here. So I get minus 1 minus c. Okay, and you can see here that the c's cancel out, right? So we're just finding the change in the value of the function. So, and we end up with 8. And that's always going to happen. If you have, if you have an antiderivative that has plus c in it, which it should, when you evaluate a definite integral, those c's will cancel out. Okay, so the answer is 8. Now, there's a shorthand notation that is typically used. So let me write that out. I'm going to write it out the way it's normally done. Notation. All right, so we're evaluating the integral from 1 to 3 of 2x dx. Okay, so rather than writing these all out as separate steps, finding the antiderivative, what we can do is put the antiderivative. I like to use square brackets. Some people use just a line. I think that's what they do in your book. But we know that the antiderivative is x squared plus c, but since it's a definite integral, I'm just going to ignore the plus c. So we're evaluating the antiderivative from 1 to 3. Okay, so this is the way it's normally written. And then we plug in the numbers. Always plug in the upper limit before the lower limit. And so we're going to get 3 squared minus 1 squared, and we get 8. So that's kind of the shorthand way of writing a definite integral, or evaluating a definite integral with antiderivatives. All right, so let's do some practice problems here. And this is just another, I think it's going to be a fairly short video, again, because it's really something that just requires practice. And, if you've gotten good at antiderivatives, then you won't have any trouble with this. All right, so we want the definite integral from 0 to 2 of 6x squared dx. So let's write the antiderivative. So I've got this 6, right? And then I'm going to evaluate the antiderivative of x squared, which is just going to be x cubed over 3. Okay, and I need to evaluate that from 0 to 2. And I can obviously simplify this and just make it 2x cubed. Okay, so now let's evaluate this antiderivative at the upper limit. So 2 times, this would be 2 cubed. Okay, so I'm just plugging in 2 for x. And then minus 2 times 0 cubed. Okay, and then when we evaluate that, this second term is just 0. And so we end up with 2 times 8, which is 16. Okay, that's all there is to it. Let's do a few more examples here. All right, so here we have t cubed. We're going to integrate t cubed from 0 to 2. So let's write the antiderivative, t to the 4th over 4, right? And we're going to evaluate that from 0 to 2. So we're going to get 2 to the 4th over 4 minus 0 to the 4th over 4. Okay, and of course 0 to the 4th over 4 is just 0, and 2 to the 4th over 4 gives us 4. All right, easy as pie, right? Okay, let's do a couple more. All right, we have the integral from 1 to 2 of 8x plus 5 dx. All right, so let's evaluate the antiderivative. I'm going to put it in square brackets. I'm going to get 8. I'm just going to leave that out there, and then evaluate the integral of x, which is x squared over 2, and the integral of 5 is 5x. Okay, and then evaluate that from 1 to 2. And we're going to get, okay, so this is going to cancel, make a 4. So we're going to have 4 times 2 squared, right? Plus 5 times 2. Okay, now I'm going to put parentheses around this whole thing, and I want to subtract the whole antiderivative evaluated now at 1. And we have 4 times 1 squared. Plus 5 times 1. Okay. So it's important to have those parentheses because, we got 2 terms in our antiderivative, and so we have to make sure that we're subtracting the whole thing, the whole antiderivative evaluated at 1. It's really easy to get sign errors otherwise. Okay, so let's evaluate this. 4 times 4 is 16, and then plus 10, and then here we have minus 4, right? And then we have also minus 5. So if I put that all together, I get 17. All right. Here's another one. Let's do this. All right, so we want the antiderivative of 8e to the 2t. So we'll just stick the 8 out here, and then we're going to have 1/2 e to the 2t, evaluated from 0 to 1. All right, so let's plug in the limits. So we're going to have, now this I can make into a 4. So I've got 4e squared, right? Just plugging in 1, right? I always plug in the upper limit first. And then I'm going to have 4 times e to the 0. Okay. And of course e to the 0 is 1, so I'm just going to have 4e squared minus 4. Okay. Now, I believe in this problem set, I didn't say it. So sometimes, oftentimes, these problems will ask for exact answers. Okay, so this is an exact answer. Okay, and the reason they do that is because you could easily plug this into your calculator. You know how to plug this into your calculator and get a definite integral. You wouldn't have to go through all this process, but that's not what that sort of defeats the purpose of what we're trying to teach here. All right, so if they ask for exact answers, then you want to have exact answers. So they're going to be answers that are in terms of, it might be in terms of e or pi or the square root of 2. You know, there might be some irrational number involved. So if you try to calculate it with your calculator, it's going to give you some decimal approximation and not the exact answer. So if you put this into your calculator to check it, you would get 25.56 something something something, right? It has some decimals that go on forever. And so that is not an exact answer. This is a decimal approximation. Decimal approximation. Okay. So just beware, especially on Wiley, if they ask for exact answers, you got to give exact answers. Okay. Same way on quizzes too. If I ask for exact answers, then you got to give exact answers. And you know, a big reason for that is that that way you can't cheat and you use your calculator. All right, it's only got one more problem. So I mean, it's just practice is all it takes. So this is just more of a word problem, but it's nothing new here. This just says write the definite integral to represent the area under the graph f of t equals e to the 0.5 t between t equals 0 and t equals 4. And use the fundamental theorem to calculate the area. Okay, so to calculate area, we're going to do the integral, a definite integral from 0 to 4 of the function, right? E to the 0.5 t dt. Okay, and so we just need to find the antiderivative. So we get 1 over 0.5, and that's 1 over half, which is 2. E to the 0.5 t, and we're going to evaluate that from 0 to 4. Okay, so we have 2, 1 over 1/2 is 2, e to the 0.5 times 4. Okay, we're going to evaluate the upper limit first, and and then I didn't mean to write an equal sign, I meant to write a minus sign. So and then we have to evaluate this at the lower limit, which is 0. So we have 2 e to the 0.5. I could write it out. 0.5 times 0. So that's just e to the 0, which is 1. Okay. So what we're going to end up with is 2e squared minus 2 times 1, which is 2. Okay. So again, this is the exact answer. Right, so be on the lookout if they're asking for exact answers. This would be exact. And if you want a decimal approximation, you get 12.778. Okay, so if you were to put this in your calculator, that's what you get. And you would also get it if you plugged 2e squared minus 2 into your calculator. So you can use your calculator to check these problems. Okay, so but just be aware if they ask for exact answers, give exact answers. All right, so the rest is just practice. All right, so take a look and do these practice problems. And I guess there's a couple of things maybe to make you aware of. You know, some of these you probably need to use the reverse power rule on, and so you might want to manipulate the, like if I this number e is one where you're going to have to do a little algebra before you can use that reverse power rule on it. And other than that, this is another area problem, and just beware there's no upper and lower limit. There's no limits of integration given. So if we're looking for the bounded region given by this, you know, between this parabola and the x-axis, you need to figure out where this parabola intersects the x-axis. So you need to find the x-intercepts. But other than that, it should be fairly straightforward. So we'll talk to you later.